Hello everyone. Right now I'm going to record homework 2.4-15. Alright, as we can see, this is the plot where we can see one bar and two forces P that are gonna be pressing this plate in between two pipes. The pipe 1 that is on the top, the thinnest one, would be steel, and the pipe 2 that is in the bottom from C to B would be aluminum. Alright, here we have the free body diagram of this system where we have the reaction acting on A from pipe 1 to the wall, and the reaction acting on B from pipe 2 to the wall. And here we have the two loads P that go down. Good. Each of these pipes, because it has a different material, has a different modulus of elasticity. As we can see here, it's labeled as EA and ES, modulus of elasticity of the steel, modulus of elasticity of the aluminum. The area of the aluminum, the area of the steel. Good. Now, we need to use the equilibrium equation. We know that by the equilibrium equation, sorry about that, we know that by the equilibrium equation, the reaction in A plus the reaction in B is going to be equal to 2 times the load P. Correct? Now, we need to find the compatibility equation. That relates the elongations of each one of the pipes. By that, we have this. That the compatibility equations would be the elongation from A to B for the whole system is equal to the elongation from A to C plus the elongation from C to B, the elongation of its parts. Because we know that the system is between two walls, it's not gonna elongate. So the elongation of the two pipes added together has to be equal to 0. Alright, so first we calculate the elongation in AC. Alright, and we have that the elongation in AC, so in the steel pipe, would be equal to, well, we know that the formula is load times length divided by modulus of elasticity times area, right? So in this case would be the following. The reaction in A, that is the one that is acting directly on pipe A of the steel, times the length of the steel over the modulus of elasticity of the steel times the area, cross-sectional area of the steel. Good. Now, we do the same for the elongation from C to B. The elongation from C to B is the elongation of the aluminum. Okay. Here we have the elongation of the aluminum minus the reaction of B times 2L divided by the amorphous velocity of the aluminum times the area of the aluminum. 2L because it's the length of the aluminum minus the reaction of B because it's the force from the aluminum to the wall, which would be contrary to this. And now we just need to add these two and equal them to 0, looking at this compatibility equation number 2. And after, we can find one of the reactions in terms of the other, okay, which I will put next. So as I said, the reaction of A times the length divided by the amorphous velocity of the steel times the area of the steel minus the reaction of B times 2L divided by the amorphous velocity of the aluminum times the area of the aluminum is equal to 0 because we're adding these two elongations. And after that, we find the reaction of B in terms of the reaction of A. And that's what we have here. That's good. Now, what we can do is substitute this new reaction of B, that is in terms of reaction of A, in equation number 1, that is the equilibrium equation that is here at the top. This would be really convenient. So everything now is in the same, so everything now is calculated, so we can find the reaction at A in terms of the amount of elasticities and the cross-sectional areas and the load. Okay, so we will have this, right, replacing RB instead of R in the equation number 1. And after that, when we simplify, we will have the reaction of A is equal to the following. The reaction of A will be equal to 4P times the amorphous velocity of the steel times the area of the steel divided by this sum. And if we go back in the equation, we can find the reaction of B, going back to this equation, right, replacing this RA in here, and we will find this for RB. So now RA and RB are in terms of all the other variables that we have in the problem. That's good. Now we need to find the stress in the aluminum, the actual stress in the aluminum. That would be part A. The actual stress in the aluminum. In order to do that, we'll have to find the force that is acting on the aluminum, which would be, if we go to the graph, would be RB, right, divided by the area of the aluminum. All right, so we will have to replace this whole expression, RB 2PE, divided by the area of the aluminum. Okay, so if we do that, we will find the following. Simplifying all of this, we will find that the stress in the aluminum will be equal to 2 times the modulus of elasticity of the aluminum times the load, P, divided by modulus of elasticity of the aluminum times the area of the aluminum, plus 2 times the modulus of elasticity of the steel times the area of the steel. Now we do the exact same thing for the actual stress for the steel, and we will find a similar equation that I will just put for you to see. The math is something you guys can do on your own, simplifying everything. So now we have the stress of the aluminum and the stress in the steel. Good. Now they're giving us some magnitudes for these. First, we needed to find it using the variables, find out 2 formulas for the stress in the aluminum and the stress in the steel, and now they're giving us the magnitudes of the areas of the aluminum and the steel and the modulus of elasticities of each one of them. So they're giving us these following data. We have now the 2 areas and the 2 modulus of elasticities in psi and in inches squared. Well, in inches squared and psi respectively. Sorry, I went backwards. And now we just need to calculate the area of the steel, the stress in the steel and the stress in the aluminum, just replacing it in the 2 formulas that we had before. So first we do the aluminum, because that's the first formula we have. So by replacing it into this formula, we'll find that the stress in the aluminum will be 1,611 psi approximately. You know, I rounded the numbers. And the stress in the steel would be approximately 9,346 psi. Alright, so the difficult part in this problem was to find all of these descriptively, you know, using the equilibrium equations and the compatibility equations with the elongations between these 2 pipes. But after doing all the heavy work and finding the reaction forces, as we have it here, we can easily find the stresses, the stress formulas that we have here, and in part B replace the data and find it in numbers. So thank you so much for listening. Have a great day.